Well, yeah, so welcome to this Google Hangout that is organized by the CESAR team here at the European Space Astronomy Center of the European Space Agency. The CESAR initiative is an education initiative which is run by ESA, INTA, and ISTF. And our goal is to promote space and science and technology to young people. And for that, we're doing several things I can show you here on the screen. So it's an initiative that is trying to get young people interested in technology and science. And so for that, we have our own instruments. We have telescopes. So you can see here we have 2 night telescopes, we have a radio telescope, and we have a solar telescope. And we will talk today principally about the solar telescope. We have a control center here from which we can control those telescopes. And we have some more installations like 3D printers. And what we are doing are principally lectures for children that are coming here every Wednesday and Thursday morning to do special exercises with us, with experts here at the European Space Astronomy Center. We are doing also courses for teachers, for school teachers, and we have online what we call science cases, which are interactive exercises where you learn about the universe, space, astronomy, and technology. And but today we will talk principally about the sun and our solar telescope. We have one which is here installed fixed close to a building, to the D building here at ESAC, and is normally working every day when the weather is good. But we have also a second set of telescopes which are exactly the same, and they can be moved. And we were using them in the past to move them to Australia and to Svalbard in the north to observe the transit of Venus. And we moved them last year to Tenerife and to Chile, to the European Southern Observatory, to observe the transit of Mercury. And today we have another big event. We have a solar eclipse. And this solar eclipse is visible principally only in the United States. And therefore we have a team of 3 people that went there. And in this Google Hangout today, we will like to transmit the images, first of all, live through the Google Hangout and also through our webpage at CESAR ESA Int. So if you want, you can connect there and see the latest images. And we also want to talk a little bit about the sun, about the history of solar eclipses and why they were important in the past and why they are still important today, also from the scientific point of view. And we also want to talk to the people there and have a kind of interactive event today. So also with some guests here that I will present in a moment. And there's also the possibility to send Twitter. So we have a Twitter feed, which is called hashtag CESAR Eclipse 17, where you can send your questions. And we have also 2 Twitter accounts. One is the CESAR, which is called ESA_ESA_ EN for English. And we have one which is called ESA_CESAR_ES for Spanish, if you want to send your questions to us. And with this, we can come to the first speaker here, which is David Parrado, who has done a presentation together with our CESAR trainee, Guillermo Infiesta, who David will talk to us about the solar eclipses a little bit in general, how they work and why they occur, and also a little bit from the historical point of view, why they were interesting in the past. And so with this, I present you David Parado. He's a researcher at INTA, at the Centro de Astrobiología, here also in ESA situated. And so I pass the microphone on to him for this first presentation.
So thank you very much for the invitation to talk here today. And I would like to start first with an overview about what is an eclipse, in particular solar eclipse. So can we go to the presentation? So we can go to the first biograph actually, and we are going we see here different types of what we can see in different moments and on different types of eclipses. In fact, an eclipse is just an occultation. It's a projection effect, and it happens when the moon intersects the field of view of the sun. So actually, it could be a total eclipse, like today in the United States, in the central part of the country. In other areas, it's going to be partial because the moon is not going to hide completely the surface of the sun. And eclipses, in fact, they happen because something that is a curiosity. The sun, although it's much bigger than the moon, covers the projection. The angular projection is essentially the same value. And depending on the relative, since the orbits of the Earth around the sun and the moon around the Earth are not exactly circular, there is small variations on the angular sizes. So sometimes the moon is slightly larger than the sun, so the eclipse is going to be total. And if the moon is slightly farther away, then the eclipse is going to be annular. But in principle, the moon could cross. If we go to the next, actually, I would like to go to here. So this is a representation of how the moon is projecting the shadow because it's in front, it's in the middle of the path. But in fact, what we are going to see today is this process of occultation and how the moon is eating step by step part of the solar disk, and the phenomenon lasts actually a significant fraction of time, but the actual total eclipse is only going to be very short, a little bit more than 2 minutes. And as I was saying before, not this one actually, this is a projection effect. In principle, a solar eclipse, it should happen once a month when we have a new moon. But in fact, it doesn't happen because the orbits of the Earth around the sun and the moon around Earth, they are not coplanar. They are not in the same plane. There is a small inclination of around 5 degrees. So only when the moon is in what we call the nodes, is the intersection, the line of intersection between both planes, this phenomenon could take place. So there is a combination of factors, how the orbit is being produced, and also how this shadow is going to be projected on the Earth surface. And this particular case, the Americans are going to be very lucky because the projection happens to be there. And in other places, it's not visible or just barely visible, like in northwest of Spain, just for a few minutes, because this projection effect. So I would like to discuss a few things about why it has been important and when was the first time an eclipse was recorded. As far as we know, the first record happened to be in Mesopotamia, in the what is now Iraq, and there, 4,000 years ago, actually, a little bit more than that, in 2332, before our era, a king of a city called Akkad, Sargon. Actually, is very important because it was one of the unifiers of one of the big empires that actually shaped the culture, the local civilization. Well, in one of these clay tablets, it's written in an ancient language and in a very different script in cuneiform, there is a sentence that actually really describes a solar eclipse that actually happened during a battle. In this area, actually, the people were pretty smart, and they developed the first mathematical computations and a very sophisticated astronomy. And along the years, they developed a theory of how the planets, the sun and the moon, were moving on the sky. So they were able to predict, not only to describe what was happening, but also to predict when eclipse was going to happen and where it was going to happen in principle. So lunar eclipses are easy to predict just because they are observable at the same time on the whole planet. Solar eclipses are much more difficult to predict because of this projection factor. Only the total eclipse only happens in a small fraction of the Earth's surface. But as I was saying, these people were able, with different systems, mathematical systems of describing the movement of the moon and the sun, they were able to predict this phenomenon. And here we have one of these clay tablets describing the movement of the moon. As I said, it's quite sophisticated, the mechanism, the theory that is behind. And there is also a representation here of several stars, the moon, and the Pleiades. Actually, these three elements, the Taurus constellation, the Pleiades in Taurus, and the moon, have been very important from the historical perspective. And from that theories, these primitive theories of the Babylonians, has been quite interesting that the moon and the eclipses and the movement of the sun have been very important in the development of the science, specifically during the 16th, 17th, and 18th centuries. The description of the movement of the moon, that is quite complex, actually. It's not as easy as we can think. There are very subtle points. And how it has been studied has been a key element in what we call the scientific revolution. The first sophisticated description of the moon was carried out by Galileo Galilei in this small book that he published in 1610 when he was using for the first time the telescope. He saw a much more complex moon that he was expecting, with the mountains and shadows, and something that people didn't know at that point. But immediately, even during this century, people were able to get a very accurate description of the moon, and also Galileo at the same time was able to observe the sun. We have to be very careful observing the sun because it has been done properly to protect the eyes. It's something that we have to remember and to remind all the time, that the sun also have spots. So both bodies are not perfect as people believed before them, but they are quite imperfect, let's say. And going back also to these historical records, also in one of the, from my perspective, one of the most important books, most influential books in the history of Western literature is the Odyssey by Homer, or some people like him, because we really don't know who wrote this book. And in this voyage, coming back from after the War of Troy, there are very interesting descriptions of the knowledge at that time around the 9th century before our era. But there is a mention also of a possible solar eclipse. So it could be the first time that in the West a solar eclipse has been described. And some specialists have tried to pinpoint, to determine when this eclipse could have happened. And in principle, it seems that it took place in the year 1178 before our era. So it was one of very interesting facts about this book that we have been able to actually recover a lot of historical information just when people thinking that it was just mythology, and it's not. There are quite interesting science, history, and also astronomy in this book. Going a little bit further, what we know, the first predictions of solar eclipses, there is one possible prediction that was made by Thales of Miletus, but actually it would be at the beginning of the 16th century, but probably this also happened during a battle in Anatolia. But we think now that he didn't predict, he just explained what was going on, what was happening. And the first real prediction, at least in ancient Greece, happened at the beginning of the 4th century by an astronomer that is not very well known, Helicon of Cyzicus. But this thing was recorded just because the philosopher Plato was visiting his city at that time, and this information has been able to reach us. So
perhaps we should switch for a moment to perhaps we should switch for a moment to the team in the United States, because we're about to have the first contact, and then we finish the presentation. Do we have them live, David? No? No live Google Hangout for the first contact? No? And then we continue until we have them.
So then, after the Roman Empire fell, we had what we call the Middle Age, a dark age for science and for knowledge. But it's not actually so dark. Knowledge was still kept in small places, and astronomy was a science that was very important at the time for different reasons. And although some people believed at the time that the moon, the Earth was flat, and the knowledge that was accumulated during the ancient time partially disappeared. There are very interesting books, very interesting studies in that time. Actually, it's this one. Several astronomers. No. This one. One British, English astronomer, let's say, that worked in the University of Paris, that it was very important in the 12th, 13th, and 14th century, wrote a very influential book that it was described, it was compiling all the astronomy at that time. He was able to explain again why the moon had phases. And then we have this beautiful diagram here that illustrates his book. And the reason of the eclipses. And as I mentioned before, why it didn't happen every month when we have a new moon. At that time, the instrumentation was quite primitive. This illustration actually gives us a view of how an astronomer in the 16th, 17th century would be able to measure angular distances. The example actually is using the moon to try to locate a point on the planet. And this was another key element for this scientific revolution. What is called the problem of longitude was one of the engines that was key in these advances in the 16th, 17th, and 18th century. And one of the solutions actually was proposed by Hipparchus, an astronomer, a Greek astronomer, in the 12th century before our era, using the eclipses. And actually, he was able to measure the relative position of the two different points on Earth around the Mediterranean basin. And although from the theoretical point of view was a mechanism that it was possible to be used for the determination of positions on the planet, it was very complicated to apply. And since they are not very common eclipses as we see today, actually they cannot be used as often as we would like. The astronomers at that time had to develop other mechanisms, had to improve the theory of how the moon moves around the Earth and how Earth also moves around the sun, to be able to really create a theory, a complete theory, and to be able to really measure positions on the planet. What we are going to see here is this wonderful eclipse in the United States. And this is the description of how the shadow of the moon is going to travel on the continental United States. And hopefully we are going to have a very nice view today of the phenomenon.
Yeah, many thanks, David. Many thanks for this introduction to the solar eclipse from the historical point of view. So we are ready to connect now directly to the United States. Yeah, I hope. Can we see it? No, not yet. Yes, I can see it. David, can you switch to the live image?
No.
So I have to say also that this is a semi-professional event, because we are doing this. Most of us are doing this as volunteers in their free time. So if you want to have a nice, super professional thing, then you probably go to the NASA page. But I think we're doing our best to show that in an adventure style, you can do quite some interesting things with resources. And so we have a very small team in the United States with 2 telescopes, several cameras. And if the communications infrastructure in the United States is holding and not collapsing under the load of people, of the millions of people that are probably watching now or trying to watch the solar eclipse, we should be able to have a connection to the hangout. Our producer here, David Carreras, is struggling to get it. Yeah, if I click it, nothing happens if I click here on my now here.
No, they are connected.
Website images. Yeah, but
no, Miguel, can you hear us?
Keeps on going. No, they said can we go live and tell me. Tell here when you're ready. Exactly. Okay, so I said.
We're ready. Tell me when we start, okay? Tell me when we go live, okay? We're all ready here.
Tell me we are waiting. And now live. Now live.
Nice live.
Hello, Miguel. Yes.
Power off, shutting down. Why? No.
We can see bits and pieces here.
No, si lo estoy cargando. Pero si lo está cargando.
Can you hear us? Yes, yes. So we can see very nicely here from our two telescopes. So you can see here on the left side, you see an H-alpha telescope. This means this is a special solar telescope which observes the sun in a very special band from the hydrogen line, which is called H-alpha. It has this typically orange glow that you probably know from the pictures of the sun that are normally transmitted. And you have also on the right side an image with the visible light, which means just normal light as our eye would see it. In this case, there's a solar filter in front of the telescope, which just blocks 99.9% of the light so that we don't burn the cameras in this case. And let me just remind you at this stage, please never look with the unprotected eye into the sun because you will damage your eyes permanently. So these are the live images that we get from the United States. You can see the date and the time when they were taken on the right upper corner. So I'm very happy because it seems to work. Yes, absolutely. You're right. So the time that you see there is the universal time. For those of you that are not so familiar with the different times, so since we're all sitting on a globe which is rotating, essentially what is important for everyone is the solar time where you're living. And to make it easier, the world is divided into 24 time zones with times. And in science, what we do to work together without problems is we define one standard time for everything, and this is the so-called universal time, which is the same as the Greenwich Mean Sidereal Time, which is the valid time for the zone around the Greenwich Observatory in London, which for historical reasons has defined the time for the whole planet. And so it's very nice to see the live images. Do we have a Google Hangout? So it seems that the Hangout, for whatever reason, the live connection to the team there is not working. So they say in 10 minutes we will try to connect again. So perhaps in the meantime we can continue with
Dice que pasamos del palo, ¿eh? Que, sí. O sea, si no sale, pues no sale. Lo dejamos ahí para que lo vea la gente y ya está. ¿No?
Y tomamos unas imágenes
Vamos
cuando
tomando
llegue.
imágenes.
Eso es.
David, shall we connect or shall we go to the next talk? David? Okay, so then we continue with the next talk, which is our colleague here, Annick de Groof. She's Belgium. She's a scientist working in Solar Orbiter, and she's so nice to give us several talks today. And the first one will be about the sun and the latest science and science results, or in general, more introduction. Okay, let's say so a kind of introduction to the sun in general.
Okay, I hope I'm sharing my screen properly. Yes, I think so. Okay, so I'm Annick de Groof. I'm working for Solar Orbiter, a mission to be launched in a few years. You will hear more about that later. But now I would like to give you a small introduction to the Sun, which is, of course, the main player in this event today. So first, most important, of course, the Sun is a star. And we shouldn't forget about that. It's also a special star for us because it's our star. It's the source of light and energy and thus life on Earth. It's actually a very ordinary star, so it's not particularly big or small, old or young, but it's just much closer to us than all the others. And so that's why actually for us it's a very important and very different one. A few facts about the Sun. It's 4.5 billion years old. It's located 150 million kilometers away from the Earth, and it has a diameter which is a bit more than 100 times the Earth diameter. It weighs more than 300,000 times more than the Earth. So the Sun is actually the core of our solar system, and so Earth rotates around the Sun like the other planets. So what is it made of actually? What are the basic elements? What's the chemical composition of the Sun? Well, it contains the same basic elements than the ones we can find on Earth, but in very, very different quantities. So on Earth, the most common elements are oxygen, magnesium, silicon and iron, as you can see here on the left-hand side. In the Sun, on the other hand, we have more than 90% of hydrogen, about 9% of helium, and only a tiny bit is left. And in this tiny bit, you do find most of the common Earth elements, but so they are in much different proportions than what we are used to find on Earth. Now, what about the state of this matter? Because on Earth, we are used to solids, liquids, or gases, but actually Sun's matter is neither of those, but it is plasma. It's the fourth state of matter, and it's actually the most common one in the universe. What's the biggest difference? So between gas and a plasma, for example, well, both of them will take the full space that you give the material. But if you add a bit more heat to gas, then actually the atoms will not longer be neutral, and the electrons will split from their nuclei. And so the difference then is that this plasma is a plasma of charged particles. So you have ions and electrons, and these are very dependent on magnetic fields. I mean, they will be shaped by magnetic fields. So what do I mean? If you have a magnetic field line, so if you have a magnetic field in a plasma, then a particle has to follow this magnetic field. It can no longer move freely, and so all the charged plasma particles will move along the magnetic field lines. Okay, now if we go to the Sun and we look at how the Sun looks like, or what the main characteristics are, well, from Earth, we can see the Sun differently through different glasses. So we have different means to look at the Sun, and in each of those means, you will see the Sun slightly different, and you will also see some different characteristics of the Sun. And mainly then, when I talk about the Sun, then I talk mainly about the surface and the atmosphere of the Sun. So the most common view, of course, is visible light. If we don't use any filter whatsoever, and we just look at the Sun with naked eye, well, I should say, of course, not straight to the Sun. You need to have a filter that will block most of the light, that you only have a tiny fraction left, so that you don't burn your eyes. Then you see a picture like the one you see here, which was taken through a telescope from Earth with a solar filter. So a solar filter that only blocks most of the light. What you see here are some dark sunspots, and I will tell you a bit more about it. If you zoom in, so if you use a telescope with higher magnification, and you use a video, so you take several images, then you actually see a sunspot like this. So here you see the sunspot umbra, which is the core of the spot. You see the penumbra, which are those lines here, and you see convection cells. Now the convection cells actually show you what is happening underneath the surface, because what we see here in what we call the photosphere is what we also call the solar surface, because we can't see deeper into the sun. Now you can see from these convection cells what is happening underneath, because underneath you have a big convective layer where actually plasma is bubbling upwards all the time, and this is what you see in this pattern. So a bit more about the name of this layer. So this is the photosphere. Photo stands for light, because that's where all the visible light is coming from when we look at it from Earth. And this is also what we often call the solar surface. It's quite a thin layer, but a very dense one. So it's only 500 kilometers thick, and it has a temperature of about 5,000 degrees. And the sunspots there are cooler, and that's why they show up dark. So they are about 1,500 degrees cooler. These sunspots, or the sunspot groups, they live from a few hours to a few months, and occasionally they become huge. Here you see an example of a sunspot group taken in November 2014, and this is the biggest one of the last 2 decades. And you can see, just as a comparison, you see Jupiter and you see the Earth size compared to this group of sunspots. So this is very quite exceptional view here. What we see today is this. So you have seen it briefly already from the live images in the US. We currently have several sunspots here, close to the center of the solar disk. And we also have sunspots here close to the limb. So the limb is the edge of the sun. And they are a bit more moderate in size than the huge one that we saw here in 2014. Okay, now let's try to look at the sun in a different way, and let's try to use a different filter. So now if you use, for example, a telescope with a filter called H-alpha, you actually see the solar light that is emitted in that particular, by that particular element, so in a particular band of light. And now we see the sun very different. What we see now is actually the chromosphere. And the chromosphere has this nice red color, and it also has a few very nice features. What you see here at the edge, and you also see it in the still image here, is a prominence, which is coronal material, solar material that is held up by the magnetic field. You also see spicules, which are these hairy kind of things, where you see the plasma continuously actually moving upwards, sometimes falling downwards, and you see these typically above the poles. And in this particular image, you also see the solar rotation. Now, this one, of course, is sped up. If you look at the sun from Earth, then the sun rotates around its axis in about 27 days. But it depends actually whether you look at the equator of or the poles, because they rotate with different speeds, as I will show you later. So this layer is another layer of the solar atmosphere. It's lying above the photosphere, what we just saw. It's a less dense layer, and it's about 2,000 kilometers thick. And suddenly it also has a much higher temperature of about 20,000 degrees. Why is it called chromosphere? Because of its beautiful color, because chromo means color. Now, there must be more, and you all know about that, because there are events from time to time called solar eclipses, where suddenly you see a completely different view of the same sun. So during a solar eclipse, the moon shields the bright light from the photosphere, and something magically happens, because suddenly you can actually see the outer layer of the solar atmosphere, which is called the corona. And the corona shows up only when the moon completely blinds the photosphere, and it shows up as this crown of white light. If you look closer and you use several images which you stack up, so you actually try to get more details out, then this is what you see. So you see really myriads of very fine detail. You see a lot of these streamers coming out. You also see pieces of the chromosphere, which you can see here. So these red things are again the prominences that we saw earlier. And you see, of course, the extended solar corona. It may not be obvious in the Google Hangout, but in this particular image, you can even also see the moon, which is being, which gets some light actually reflected from the Earth. So this particular image was taken in 2014 or 15, if I'm not mistaken. Okay, so why do we see such different things depending on how we look at the sun? Well, actually, light is composed of many different colors, as we know already from Earth, but not only colors in visible light, but there's a very wide spectrum of different wavelengths. So light is a kind of wave, and depending on the period of the wave, you see light very different. And visible light is only a tiny bit of the whole spectrum. So if you go to longer periods, you have infrared light. This is more, we feel that more like heat. You have microwaves and you have radio waves. When you go to shorter wavelengths, you get ultraviolet or extreme ultraviolet, X-rays and gamma rays. You can play a little bit with these different types of light also on Earth, because we also have special cameras like X-ray cameras with which you see different parts of, for example, your body. So if you look with an X-ray camera to your body, you use X-ray light, then actually you see all the bones. The image here in the middle is using infrared light, where the hottest parts of your body will show up brightest, and the cooler parts like fingers will show up darkest. So why do we need solar telescopes in space? I have already shown several characteristics of the sun, and we could all kind of see them from Earth. Of course, you need telescopes, but why do we want solar telescopes also in space? Well, from Earth, we can only see a tiny bit of this huge spectrum, and the sun is actually emitting light in many, many more colors or wavelengths than the ones we can see from Earth. So here you see the same spectrum. Now the shorter waves are on the left and the longer wavelengths are on the right, and you see which ones can reach Earth. So only visible and a bit of the ultraviolet and infrared, and also a window around the radio waves. But you can't see any extreme ultraviolet, X-ray, gamma rays, and so on. So that is why we want to go into space, especially to look at the corona. Because the corona is extremely hot and it emits light that is filtered by the atmosphere, mainly because it has very short wavelengths. So it's in this part of the spectrum here. This is what, well, I think a very, very nice image that shows a lot of different wavelengths in one image. So what you see here is just a composite of many different solar images, but all taken at different wavelengths, so with different filters. And you can see it's all the same time on the sun, so to say, but so you can see the sun very differently in each of those wavelength bands. And what you see here is just plasma, which is at different temperatures. You see sometimes plasma at different layers, so a bit higher up in the sun or lower down in the atmosphere. And so that's why, to really understand how the solar corona works, this is why we want to launch solar telescopes in space. Here I show you a movie from a small ESA spacecraft, which is Proba 2. And which has a very simple instrument on board, but which takes solar imagery all the time of the sun. So you have continuous solar imagery in one particular wavelength band. And I like this one very much because you see so nicely how dynamic the solar corona is. So this, as I told you before, it's not really true speed because it takes 27 days before the sun does a complete rotation. But you can see here how dynamic it is, and you also see so many different structures in the solar corona. So this region now, this layer is extremely hot. Suddenly the plasma here is up to millions of degrees. It has a very low density, only 10 millionth lower than the Earth's sea level. It emits light in extreme ultraviolet and in X-rays. And so this particular image is taken in extreme ultraviolet. And as you can see, it's very dynamic. So the most apparent thing are these bright regions that you see here in the middle. And this is what we call active regions. So why do we see these active regions and how are they formed? Well, this has everything to do with the magnetic field, because the sun has quite a complex magnetic field. And so whenever you have patches, strong enough patches of a north aligned magnetic field and south aligned magnetic field, you get automatically magnetic field lines connecting the two through a curved line, so through a loop, as we say. This is what we call coronal loops. Now, I've told you before, all the material on the sun is plasma. And so it has to follow these magnetic field lines. So even if you can never really see a magnetic field by itself, you can see the material following the magnetic field lines. And here on the left in this movie, you see a similar experiment with just iron particles. And so when you add a magnet close to it, then you see the same kind of curved shapes that will connect the two poles of the magnet. And so a similar thing happens on the sun. So actually the sun, when you look at a magnetic field, it's quite a complex one. And so this is kind of a simplified simulation of how the magnetic field on the sun looks like. Typically on the poles, on the north and the south pole, it's much simpler, and you have mainly a positive of negative poles, but then in between you have many of those little connections and many different dipoles, quadrupoles, and so on, where the active regions are located. This is just another nice example of a dynamical phenomena. This is called a solar flare, and you see in the left side you see a movie of it in the chromosphere, and on the right-hand side, you see a similar event, not the same one, and you see how it looks like in the corona. So this is a very, very sudden release of radiation, of energy. So it's magnetic energy that's being converted into radiation. Okay, so I told you I told you a lot about the dynamics and about the very complicated magnetic field, but it's not always the same. It also evolves over time. So the sun and the solar corona in particular is not always equally active. The plasma is confined to the magnetic field, as we saw before, but we also know that the rotation of the plasma is different at the equator as at the poles. So at the equator, the plasma will move quicker, will move faster than at the poles. Now, if you imagine a ball of plasma, you have a magnetic field which confines all the plasma, and then you start stretching these magnetic field lines and the plasma with it, because you kind of fold it over the sun because of these different rotation speeds. Then after a while, if you start from a simple dipole with a north and a south pole, after a while you have a very complex magnetic field. Because on one hand, the magnetic field lines are now wrapped more horizontally, and on the other hand, you have continuously plasma bubbling from the interior, going upwards and taking the magnetic field with it. So this is how you end up with the solar cycle. So you have times where you have a minimum activity, and you have times where you have maximum activity. And this is a nice overview taken by another ESA NASA spacecraft, which is called SOHO, and which is already more than 20 years in orbit. Well, not in orbit, it's in space, I should say. It's not in orbit around the Earth. And it shows the cycle because it shows here how the corona looked in '96 when it was solar minimum, around the year 2000 where the sun was much more active, and so the corona was much brighter because it was much hotter, and then back to 2006 where we went back to solar minimum. Currently we are 2017, and we are on this graph. This graph is actually showing you the activity by the number of sunspots, because this is something I haven't really told you before, that at the basis of these active regions here, you have the sunspot regions. And so you can see from the number of sunspots at every given time, you have a kind of a measure of the activity on the sun, and so how hot also the corona is in general. So here you see an overview from 1950 up to today, and currently we are again heading towards a minimum. And you can also see that the last cycle, the one we are currently in, cycle 24, has been a bit more moderate than previous ones. Okay, last bit, why do we all care about this? Do we actually, apart from light and energy we get from the sun, do we have any other solar influence? Well, yes, we do, because there is the solar wind, which is a continuous stream of plasma, so of charged particles escaping from the sun. And so it creates this kind of bubble in which all the planets reside. And so sometimes, well, anyway, every day, the Earth is actually affected by the solar wind. But since it's quite continuous, it's not such a big deal, except that sometimes a very large cloud of plasma can suddenly escape into space. And of course, this can also head towards Earth. And this is what we call a coronal mass ejection. And the movie has played already. But so here you see from the sun, you see a very large bubble of coronal plasma being ejected into space. Now, these images were taken from SOHO, which is located between the Earth and the sun. So this particular coronal mass ejection didn't move towards the Earth, but from time to time this happens. And this is a bit of a simulation to tell you what happens then and how these CMEs, as we call them, can affect Earth. So these charged particles move towards the Earth, and anyway, Earth is always protected by its own magnetic field. But here you can see that these magnetic field lines of the Earth are being opened up, and you can actually get charged particles streaming close to the Earth and mainly around the poles. And this is one of the reasons, well, this is the main reason why we see polar light, both at the North Pole as at the South Pole. So this is the end of the introduction. I only have a few slides left to show you what will we see today during the eclipse. Well, not us, but the people who are lucky to be in the US. So the solar corona will show up only during totality. So just before and just after, you also see the start of it. You see part of it. If you look at it through a regular camera, or by the naked eye, this is probably kind of what you will see. This is an image that I was happy enough to take myself in 2012. And then this is the view that you can get. Now, if you make many images with proper equipment and you stack them up so that you get all the detail out, then you can end up with these kind of very, very detailed images of the solar corona. And I leave this up where I show you all the different features I talked before. So prominences will show up at the side where you see bits of the chromosphere. Of course, every eclipse is different. So you may see it at different parts of the limb. You can see helmet streamers, which are these large coronal structures pointing out to the sun. And you can see coronal loops, which typically overlay the sunspots and the active regions. And this is where I will end.
Okay. Many thanks, Annick, about this introduction about the sun. So with this, we can try now to the connection to the US and see if we can talk to the guys there. So let's see if it works, if we can talk to them, because the images are coming in very nicely, as you can see on our webpage. So we don't manage to get the Google Hangout webcam direct connection. What you can see here very nicely are the nearly live images, because you can see I think now it's every 30 seconds that we have a picture. And you see that the moon advances slowly in front of the sun. So we have every minute now a picture. It's a pity that we cannot get the direct Google Hangout connection. It would be really nice. But we are already very, very happy to have the transmission of the images, because the predictions in the United States was quite some problems with the infrastructure and the networks and the bandwidth, because there are a lot of people traveling. Perhaps our colleague Don Merritt he's American, he can tell us a little bit about what they expect in the United States today from the infrastructure point of view.
This is incredibly unprecedented, so nobody is quite sure what is going to happen. The infrastructure for your internet and for your phone, your mobile phones, is sized to a normal. Thousands of people pouring into places where they don't normally, where the population is normally lower. Some of the internet systems and even the telephone systems may collapse. So we're watching and hoping. We're pleasantly surprised that we're getting video from our team in Wyoming at the moment. So things are going quite well, and we should be talking to them shortly, should we not?
Yeah, many thanks, Don. So it seems that we are really lucky, because I see here live video from the observing side. Hello, Miguel.
Are we live?
Hello, Miguel. Can you hear us?
Live? Yes. Hello, everybody. Hello, Europe. This is the team that we are in Wyoming, Casper Mountain, at an altitude of 2,400 meters, and we are having a great day here. Really, the sky is beautiful. There are no clouds at all, despite of some rain yesterday night. We had to cover all the equipment that we have behind. Have to cover it quickly last night because it started raining a bit. But it was predicted, and the prediction is also for today is what was expected. So we have a sunny day. So that's great for the eclipse. The eclipse is progressing. We are kind of halfway until totality right now. So first contact was something like 40 minutes ago, more or less. And while it's progressing well, we have all the equipment running, capturing all the images that we can. And well, I will show you a bit of the equipment we are using. So this is the two telescopes that we brought to follow the eclipse, and these images are taken now every 15 seconds. We are only relaying them to the web every 30 seconds. But these are the images that you can see in the web. Okay, we have two images. One is an H-alpha image that is a narrow wavelength close to the orange color, and here we can see very well the chromosphere of the sun. And the images are taken through this telescope with this camera, and we send them to our computers that are there behind that shelter. And there they are pre-processed a bit, because we need to reduce the size of the images, because the transmission is a problem. We don't have much bandwidth. So you can see in the screen an example of the image taken with one of the two telescopes. So we are controlling everything from this computer. The two telescopes. We have another computer here that we are also taking images through a webcam that are also transmitted live. And here we are controlling another camera. I will show you later that one. So let's go back to the telescopes. So as I said, this is the H-alpha telescope. This white one is the visible one, the visible lights. So we are taking images as well every 15 seconds, relaying them every 30 seconds at the moment. And here we can see very nicely the sunspots. There was a beautiful group of sunspots that now are covered by the moon. And they looked beautiful in the first images that we took. And there is another group at the limb that is also coming into view of the sun. Unfortunately, this one has not, let's say, not really active, so we don't see any prominences on the limb of the sun in the H-alpha. So it's relatively quiet today, the sun in H-alpha. But the images are progressing, everything is going fine with the two telescopes. The mount is tracking the sun constantly, so we don't have to care much about following it. Just a small adjustment from time to time. And that's it for the two tubes, for the two telescopes. Here, on this side, we have the webcam. This webcam is transmitting the images well, of the people around here. And we have put here a nice display. It's a pinhole projection of the ESA logo. So what you see is really the sun. So it's the sun projected through the small pinholes of this plastic that we have cut. And you can see the eclipse progressing in this way. You know? So you see many small suns, many eclipses in one image. Okay, so that's transmitted live. We have here another camera. It's a bit different from the rest. This one is a wide-angle lens, and we have it fixed, so it's not rotating with the sun. It's not tracking it, and it's taking images every 1 minute. So with this, we will have a beautiful composition of the eclipse as it progresses in the sky. Okay, so we will have into the sun, full totality, and the rest of the eclipse in one full image. Then we have more equipment. We have three more mounts, and Manuel is doing some fine checking or fine tuning before totality in one of the cameras on the polarizers. Do you want? That's the spectra. So, Manuel, can you explain these two camera sets?
Well, we have two sets of cameras. One of the cameras on this side is dedicated to produce a spectra of the sun, especially for the last moments of the eclipse and the corona. And the other two cameras, they are working in different polarizations to take images of the corona with different polarizations to see how the gases and the magnetic field interact and how they can produce different structures that you can observe. Because this is the more unknown part of the science behind the corona, how the matter interacts to have all the gases at a huge height temperature. So especially this kind of dynamics is not very well known. We are taking illustrative images. We will try to use it for science, but in principle, this is a demonstration experiment. So. And this is what we are doing with these two cameras. Okay. In parallel, we have another two cameras that are carried out by Abel.
And Sylvia. Yeah.
And Sylvia, sorry.
Yeah. Yeah, the camera here and my camera here, and we are both taking simultaneously picture of the sun with the same focal length. And yeah, we are changing the batteries just to make sure we have everything charged for the totality, because it's the main moment, the most important moment. So everything so far so good, and we are trying to see the totality.
Okay, very good. This is a little bit where we are set up. See, there are different teams over here. Very beautiful area. There's our American colleagues. Everybody's excited with our logo.
About the way how you're connecting and how you transfer everything.
Excuse me, can you repeat that, please?
Okay. How you're transmitting everything. How do you connect all this equipment?
Okay. How do we connect it? Okay.
4G.
We have the cameras attached to this equipment, of course, to get the images. If you see, there are plenty of cables. It's a bit of a mess. It's not that messy. We have been working many weeks to do this setup. So if you see, it's all connected to USB cables, to some kind of hub, and these are connected to the computers that are here behind. We are also giving power directly to the cameras, at least some of them, so not to well depend on battery that it might at some point run out of batteries. So we have full power on the mounts and cameras, and the rest basically is done by the software, the computers. So we get the images, we process them, we need to decimate them, so we only send half of the images that we are taking, and we need to reduce the size. We are getting full-size images on the cameras, something like 5,000 pixels each camera, but we are only sending around 1,000 pixels each. So we are reducing by 3 this size, and then we are compressing the image as well a bit, so that the transmission is slightly better. For the moment, the transmission is going great. We have here the screens where we see how the images are being taken and sent to the servers. And the transmission is relatively fast. It's something like 200 kilobytes per second. So this is very good. It's very good. We can transmit all that we want. The rest of processing is done at ESA, the servers at ESA. Once the images arrive there, there is another processing and rotation of the images to make them a bit better to visualize on the web, and they are then posted in an open FTP that is open to the public, so anyone can go there, get the images and look at them. They are also transmitted live in this web that we have, and they are kept then in an archive, so that in some weeks or in some years, people can use them for whatever they want. We use them in the CESAR project for education. So we have science cases based on these events, so students can go to these images and do some science that we recommend them to do, but anything that they can think of, they could be done with these images. I need to check one of the pipelines that is not working completely. So I disconnect myself for a moment, and I'm going to check why it's not transmitting the image now. See you later.
For the first impression, so we will do the next talk about the why eclipses are so important from a scientific point of view, and then we will come back to you before we reach the totality.
Okay, now it's back.
One moment.
Okay, great. They will come back before the party.
Yes. And it's about the science that can be done during those solar eclipses. It's a science that you have to do it very fast because the eclipses are very short. It's only several minutes. So let's see what we can learn in those few minutes about the sun.
Okay. Can you check whether the presentation is properly shared? Okay. So I'm just going to explain a little bit what has been done before, what's being done now, and also introduce you to some space missions which actually also take part in eclipses. So as David has said in one of the first presentations, eclipses have always been very important for science, and especially in the earlier days where we weren't in the space era and where we didn't have all the observations we currently have from the sun in space. So during the last century, solar eclipses have been mainly very important to get ultra precise measurements of the lunar orbit and also the gravitational reactions between Earth and Moon. Because of course they were models, they were calculations, but to make sure that your understanding is really good enough, actually what people did is try to predict as precise as possible when an eclipse would take place and where exactly and how it would be seen, and then check that against the model. Then in 1919, another very, very important test was done using a solar eclipse. At that time, actually, they used the solar eclipse to test Einstein's theory of general relativity. And how they did that, well, I have just one slide, so only a short introduction to what happened. Well, actually, Einstein said, okay, space and time are actually linked, and you have some kind of space-time grid which can be curved by massive bodies. So the sun, for example, is a very good example of a body with enough mass so that it can really curve space-time, as you can see here in the model on the left. Now, what was predicted by Einstein is that also light would be curved by this effect of the gravitation of the sun. So what he said is, if you have a star which is actually behind the sun, if you see it from Earth, then its light would be curved so that you could actually see it from Earth and it would look like it would come from a different direction. Now, of course, this is exaggerated, but this is actually the theory that he predicted. And of course, you can never really see stars very close to the sun because the sun just has much too bright light, except during an eclipse. So this is why they used the solar eclipse of 1919 to test whether indeed what Einstein predicted was right. And so here on the right, you see an image, an observation of a star which was near the eclipsed sun, and then you also see a red dot where actually they expected the star position. So with this measurement, they had not only proven that indeed there seems to be something weird going on and what Einstein predicted seems to be right, but also it turned out that the distance between the expected star position and the actual star observation was also exactly the distance that Einstein predicted. And they checked again 6 months later, the same star position, but without the sun in the field of influence. And indeed, at that time, the star was at a different perceived position. So that was a very, very important test. Now, since then, of course, with space age and with more and more capabilities we have, the importance of the eclipses were a little bit less than in these earlier days, but still there's a lot of science being done, and I have a few examples here. So at every opportunity since space age, we always try to relate solar coronal structure seen from ground at the eclipse with features on the solar surface. Because we can, from space, as I showed before, we can see actually what's happening close to the sun, but we can't always very easily see what's happening far away. So the extended corona can't always be imaged that nicely, and especially the link between the two. I will show you later why that's such a problem. We also try to improve forecasting capabilities. So as before, we try to predict as good as possible what we are going to see during a solar eclipse. And this time it will not be the time and the location of the eclipse, because these models are now very fine already, but we try to really predict how the corona will look like. So the solar magnetic field, coronal predictions, and also the exact timing and brilliance of Baily's beads, for example, these shiny parts that you see close to the limb of the sun that you will see in some minutes. Another very big thing is testing out new instruments for space missions that are supposed to image the corona. So I have a few examples here. So this one is a very nice example of current science data being taken during eclipses from ground. So what you see here is a composite image of many different images taken from ground, not only in white light. So you see some white structure here. So these are the typical white light images. But you also have red and green, which are overlays of different images which are taken with special filters and with spectrometers. So they are used to look at coronal emission at one particular element. So one particular temperature, also one particular chemical element. And so from the combination of those, like one of the images you see here, scientists can reveal coronal composition and temperature, and also the speed of the particles. This is an example of a simulation. This particular simulation is done on the 14th of August, so a few days ago, and it hopes to represent what the people in the US will see in a few minutes. So this is the model of what this science group thinks the corona will look like. And so for that, they use, of course, data from few weeks ago, and then they implement their models to predict how the corona will evolve in this more than a week, and then how it will look like today. So here you just see what people will perceive with the naked eye, and in this one they have tried some imaging techniques to get a bit more detail out. Same here, so this is just some image processing being done just to make sure you can see all the tiny detail that they predict. And on the right-hand side, you see a simulation of the magnetic field currently in the solar corona. Okay, then the last bits here, I also read, I don't really know many details about it. I read also about a few science cases that are going to be attempted today to detect interplanetary dust falling into the sun by searching for its faint infrared light beyond the corona. So they will be measuring the corona in infrared lines, and also to detect or observe directly the solar transition region, which is a very, very fine region between the chromosphere and the corona. Okay, now we will take a lot of imagery from ground, but we still have the solar instruments in space as well. And the best results you always get to combine those two. So also the solar instrumentation on spacecraft will observe the sun before, during, and after the eclipse. Now, I must say, not all the instruments in space will actually see the eclipse itself, or they will see it differently, for example, through a sequence of partial eclipses. And this depends on their location with respect to Sun, Earth, and Moon. So you have a crude image here. You have, of course, many satellites which are in Earth orbit. So if they are in low Earth orbit, they may orbit through the Moon shadow. And so they may see different eclipses in one day. This is the case for one particular ESA satellite, which is Proba2, and I will show you in a minute what Proba2 will see today. Then SOHO, I've mentioned SOHO before, is actually located in a point which is called Lagrange 1 point between the Earth and the Sun. Now it's outside of the Earth-Moon system, so it cannot see the solar eclipse. So it will see the Sun in total, also while at the same time we take solar eclipse images on ground. Okay, so what about Proba2? Well, Proba2 is in low Earth orbit, and so it is doing about 14 orbits during one day. And it's always following close to the terminator, which means between day and night. The line between day and night, as you can see here, this red square that's moving over the screen. It will move through the moon shadow 3 times today. And so here on the right-hand side, you see a simulation of what Proba2 will see. So it will see several partial eclipses, but no totality. I don't currently have the imagery yet of Proba 2, but I can show you what Proba saw during one of the previous eclipses. So this is an example of 8 March 2016. Maybe you already saw the moon shadow coming close here, and now it will come back. And yes, so here it is again. So here you see again the solar corona at about 1 million degrees. So these are extreme ultraviolet images taken in a wavelength band around 17.1 nanometers. So this is the kind of movie we expect later today from Proba 2. Then SOHO. So SOHO will observe the full sun through 21st of August, because SOHO will not see the eclipse as it is located, you can see it here, between the Earth and the sun. Now the scale is not quite right, but anyway, it will not see the moon shadow. But SOHO has special instrumentation on board, and it is able to create its own artificial eclipse. So not only during days like today, but all year through. And here you see a composite image. So these are mainly many images together, 3 in total. In the middle, you see an EUV image of the sun, as I showed you before. And then you see here 2 images of the corona, which are taken with an instrument called a coronagraph, which is kind of an artificial eclipse creator. So how does this work? Well, a coronagraph has an occulter in its instrument, which will shield the very bright light from the solar disk. And so you see here in the middle, this red bit is LASCO C2. So it's one of the 2 coronagraphs on board SOHO, which has a field of view from 2 to 6 solar radii. And then you see the blue one, which has a bigger occulter, and so it can see, it will block more light from the sun, and it can see then the very faint structures of the corona in white light much further away from the sun. And combining all those together, you can get a very nice view of the solar corona. Now still, as you can see here, there is still a gap in the middle. You see this black bit here, between the EUV image and the first coronagraph image, and this gap is still very difficult to fill with the current instrumentation. And so that is why even nowadays eclipses are still very valuable, because during an eclipse you get, okay, only a few minutes, but you get the opportunity to completely fill this gap. So this is a composite of Proba 2 swap in the middle, so EUV light. Then you see in gray an eclipse image, and then you see again 2 coronagraph images of SOHO LASCO. And only now you can really follow the structures on the sun through their magnetic field structures here close by, up to the CME, which will then propagate further into space. Now, the problem is, of course, eclipses only happen from time to time, and we really want to fill this gap and have imagery more often close to the sun. So why can't we make coronagraphs which can cover this inner corona? So why can't we just make the occulter smaller, so that, like the moon, you only occult the disk only, and you can see the corona immediately off limb? Well, the problem is stray light. So that means light in your instrument, which is actually following channels it shouldn't really follow, and is actually getting on your images while it's not coming from the part of the body, in this case the sun, you want to measure. So that's stray light, and also the diffraction of light around the occulter. So those 2 limit our current instrumentation, and so you can't really make small instruments which you can easily embark on board a spacecraft to look at the sun very close by to the limb. So the only solution is to make a much bigger instrument, but then you can't easily get it into space. Or you can build a coronagraph using two spacecraft. And this is a novel idea, which is the base of an ESA mission, which is going to be launched in a few years, normally late 2020. And that mission is called PROBA-3. It's actually in the same series, so to say, of the PROBA-2 spacecraft I mentioned before. And these are very little spacecrafts, but they try out new things. So it may be that for science, these are not the best ones, but they try out new ways of getting scientific relevant data. And it's the first time they try it out. So that's why it's a small mission. They try out new technology. And let's see whether we can actually make it happen. This is a simulation of how the two spacecraft will look like. So the sun is actually here on the right. And then the first spacecraft is not much more than just an occulter, which is this gray area here. And then, of course, you have some electronics. There's also a small instrument here. And you get a solar panel, which is facing the sun, of course, to get energy for the electronics. And then you have a second spacecraft, which is this one, which will have the main instrument on board, which is called ASPIX. And ASPIX is the imager that will look at the sun, but the solar disk will be shielded by the first spacecraft. So here you see the situation a bit better. So this is the spacecraft with the occulter, and this is the spacecraft with the instrument. Now, of course, the main challenge of PROBA-3 is to keep those two spacecraft at an equally spaced distance from each other and always perfectly aligned. There will be about 150 meters between the two spacecraft, and you have to get a formation flying precision of about 1 millimeter or a few millimeters to make the coronagraph as a whole working. So this is definitely the biggest challenge that PROBA-3 is facing. This is maybe a little bit too much detail for now, but so it just shows you how it will work, that it will have a very elliptical orbit, and only during parts of the orbit it will actually do the fine formation flying. And so the coronagraph will only work during about 6 hours every 20-hour orbit. So we all look forward to this new mission in 2020. Last slide I have on science is that currently there are many scientists out there in the US to try to get the best data out of the Eclipse. And I'm sure many will also be very much distracted by the Eclipse because it stays a very wonderful event. And so here I want to share with you a few pictures that I was happy to take myself during one of the previous eclipses. And I think this is still, even with all the technology now, it's still absolutely wonderful to experience such an event.
Many thanks, Anik. Very interesting. So just in continuation to your talk, we will talk to Joe Zender, who is involved in PROBA-2 and I think also in PROBA-3. And he's there live at the observing site. And so I would like to ask him, how does he, what is his experience of the direct observation there? And he fears that in the future, PROBA-3 will make those direct solar observation completely unnecessary.
Oh, hey. Oh, I have whoever listens in actually to this communication. My name is Joe Zender. Thanks, Michael, for introducing me. So we're already here. I'm very excited, actually. We still have, looking at the time, 25 minutes to go for the totality. Our computer will give us science in 10 minutes and then in 2 minutes, and we have to change filters here, so to be prepared actually for the totality. The weather is, I would say, still good. Actually, there are light clouds coming in, but I think actually we will be fine for the totality. So we are all very excited here, not only me, everybody is prepared, all the equipment is up and running, and everybody is happy, nobody's panicking. That's good. And then actually for PROBA-3,
I think since we are approaching totality, it will get more and more difficult with the bandwidth of the internet connections. So unfortunately, we lost the direct Google Hangout connection to the observing site for the moment. Just when Joe was about to explain why he still wants to go in the future to solar eclipses and not just use the future Proba 3 spacecraft. I'm not sure if we can get it back. So, so we lost the live connection, which is what we were already fearing since the beginning, since the start of the eclipse. And I think we were really very lucky that up to now we were able to have a connection. But it seems that at the moment, yeah, there's no live connection anymore. So Don was just checking if he could reach the NASA site. Sorry, we could not hear you. Can you please repeat, Don?
As I was mentioning earlier, the bandwidth in all of these sites are sized to the normal population. And now for example, in Casper, Wyoming, they anticipated that the population of the city would double or triple just during the eclipse. So we were very uncertain if we would be able to get live video or even still images from our team during the height of the eclipse, and it looks like we've lost it. And even all the NASA sites that I've checked that have live streaming at different locations across the country have gone down as well and are not working. So we're not the only ones.
Okay, so then perhaps we can use the break to look into the Twitter feeds. Did you see any reactions onto the Twitters that we have or questions so far to the Google Hangout?
Just one follower, she was following us on NASA in Paris. She didn't know which one to pick up because both of them were perfect.
We get the connection back. Let's see. Hello, Joe, can you hear us?
Yes.
Yeah. Okay, I started my sentence and probably I was cut in between there. Talking about Proba 3. So in Proba 3, we have an orbit actually of kind of day, 24 hours, with and we can observe the totality there for 6 hours basically every day. The probability to catch solar events within 6 is dramatically larger actually than having one eclipse 2 minutes or 4 minutes every year, where you have to go with all the equipment. We will have a wonderful camera with several filters and a broadband and a wide to observe this. We can run a number of campaigns then, depending on the activity, and it will probably provide us with a unique data set. But I guess people will enjoy the solar totality eclipses actually from ground and your annular eclipses and all the phenomena for us to observe. So actually, I would like to cast. We are now at 6:45, and within a few minutes, actually, we will move the protective filters. We will observe actually this kind of identical cameras. Polarization. We have to prepare for this, and I will give back actually to my colleagues.
Okay, many thanks, Joe. So we would like just to watch you, so just there so that we can see what you're doing.
Okay.
The light is changing.
You want to watch?
We will just watch you working.
Perfect, no problem. We'll be connected.
Has shown us here the playback of the fast playback of the eclipse so far that you can see now in the Google Hangout, where you can see what we have observed so far since 1 hour. We have a question here.
The countdown, 5 minutes.
Question from Brenner. Thank you very much. He was asking, do any other planets in the solar system receive solar eclipses? Which expert would like to take that? Or I could do it. Actually, a lot of them do. Any planet with satellites, with moons, will also have eclipses. Ours are quite unique here at Earth, though, because I don't think there are any other objects in the solar system, any other planets that get total eclipses the way the Earth does, simply because it's an odd universal coincidence that the relative size of our moon is almost exactly the size of the sun. So while all planets that have satellites or little moons around them will get partial eclipses, we live on the only one that gets a total eclipse.
Yes, absolutely. So it's a very fascinating fact that if you would read this in a science fiction book, that there's a solar system where a planet has a moon that has apparently the exact same size as its star, whereas where the planet is orbiting, then you would say, what a stupid invention of the science fiction writer. And we have exactly this with our Earth and the moon system here. So a very curious coincidence. And what you can see on the Google Hangout is now the normal visible light images and the playback of the eclipse in several minutes compressed, or in several seconds compressed, what we have observed so far since we started the observation. So it's quite impressive. So what you see here are really images that were transmitted live from the United States. You can also see that in the beginning, the first image, there's a problem with the processing, because when we take an image, then it's transferred here to a server here at ESAC, where it's then processed to produce the final image that you can see. And of course, this has to be coordinated. In the beginning, it took much longer. The transfer took much longer than the processing of the image. Normally, it's always the other way around, because the transfer is quite fast if you have a fast connection, and then you need quite some time for the processing. In this case, it was different. So you can see at the beginning of the loop, you have a kind of half image, because when the processing started, there was only half of the image transferred yet. And I don't know if we have a live connection to see what's happening there in the US. So we can see now our team
now, and the light is dimming a lot. Birds are stopped. It's really dirty. And we are going to have a great thing. We have a bit of cirrus, but not. Wow, this is really amazing. Oh wow. Okay, the automatic sequence of this we will stop the transfer of images in totality, but we will resume it afterwards. We'll go into a relief mode that we cannot transmit at the same time. I will now, start up and show us the view.
On the live image, there is less light. The light is dimmer, so which is really amazing to see. We can see it even on the video stream on the bad quality, that there's less light now illuminating the scene. And if we take a look at the live image, what is the last image that we have? Is from 1734. So we are missing some images. So probably we have transfer problems because we are already at 42. The last processed image is from 34. So we should be much closer now to totality. Essentially, it should begin any moment. So I think they're pointing to the sun. Oh, it's getting dark. It's getting dark in the US, so I think we're starting the totality. Very impressive. So we also have the communications problem. Yes. Oh.
Wow. It's incredible. Get it in the hands.
But I have to say, I'm really because I didn't think that we would see this type of images at all.
I was pessimistic, I think. I had no expectations. But the totality here in Casper will last approximately 2 minutes and 40 seconds.
Yeah, unfortunately, we don't get the images at the moment. So we are stuck at images from minute 32. It's probably because of the bandwidth problems. And our colleague here, Santa Martinez, from her holiday, sun is back. So you can see that fast. What I was just trying to say before, so Santa Martinez, who is controlling the processing on the server, just wrote on the WhatsApp group that there are problems with receiving the images. So I hope we can get connection better. So hello in the US, Miguel, Dario, Joe. Can you please show us a little bit of the ambience there and give some comments about the so while they're still trying to get themselves together, we have another question.
Yes. Miriam is asking us whether it's Mercury so close to the dark images. Just together with Eclipse at the left, is it Mercury?
Oh, I would have to check. In principle, yes, during the totality, Mercury, Venus should be visible. So, because Mercury is always very close to the sun, so I suppose that Mercury should be clearly visible during the totality because it's quite close to the sun always. And Venus, in this case, it's also quite close. So I cannot really say if on which image. I don't think that it's so close that we could see it on our images, but we don't have any images at the moment. But I would say yes.
I would say if you see it on these images, it's probably Mercury.
Yeah.
Because the other ones, I believe, are going to be further away.
So it's which distance? It's yeah.
Yeah.
Okay, yeah. So people that are there should have been able to see it clearly in the sky. And I don't know if we have a connection. So the connection is still quite bad. We have no audio and no video for the moment. Yes. So I think what is happening now is that everybody takes the pictures that he took with his smartphone and is uploading them to Facebook, which of course doesn't help us. And I see, unfortunately, our live images are still at 1734, 10 minutes before the totality. So what our people are trying to prepare now is some nice images from totality from the other cameras, which were not live, and then transmitting those to us so that we can show them to you. I would say in the meantime, since we had some questions, we can perhaps go to the next presentation. Anik, if this is okay for you, then we could go to the last presentation about science and the sun, which in this case is about a spacecraft, which is about solar orbiter, and what the scientific goal of the mission is and how it should be achieved.
Okay, so the third presentation is indeed on Solar Orbiter. So that's the mission I'm working on currently, and we are preparing a spacecraft that will orbit the sun, as the name says. And it will not just orbit the sun, because that's what the Earth is doing as well, but it will actually come very close to the sun and then at times also go very far. And it will also look to the sun from a very different viewpoint, and it has a very interesting set of instruments on board. So I will show you a bit more about the mission. The main goal is to explore the sun-heliosphere connection. And what do I mean with the heliosphere? The heliosphere is actually the whole bubble in space that's being influenced by the sun. So the sun has this continuous stream of solar wind, of energetic particles, well, charged particles. And so it will influence all the planets and beyond. And so this whole bubble is called the heliosphere. First, a bit about the mission itself. It is the first medium-class mission of ESA's Cosmic Vision program, and it's implemented jointly with NASA. It has a dedicated payload of 10 remote sensing and in situ instruments measuring from the photosphere into the solar wind. So remote sensing means, actually, to say it bluntly, it's a kind of camera. So it looks at the sun from a distance, and it actually takes images or spectrometers from the spacecraft looking at the sun, while an in situ instrument is an instrument that takes data really close to the spacecraft. So it's kind of feeling what the plasma the characteristics of the plasma close to the spacecraft. So it's these kind of instruments that will actually measure the magnetic field close by, that will measure any waves that will pass by, and energetic particles as well. So these are the ones that are measuring the solar wind. What is the main goal? As I said before, understanding how the sun, and in particular the solar wind, influences its surroundings, and its surroundings also means the Earth, of course. Here on the right, you see 3 missions, which have been all 3 very, very important for solar physics. The first one being Ulysses, which was the first one to go over the poles of the sun. It has given us a lot of information about the solar wind, but unfortunately, it only had in situ instruments on board. So it did feel and measure the solar wind on the spacecraft, but it never really came very close to the sun, and it didn't have any cameras on board. Then SOHO is the observatory, which is already more than 20 years in space, which has been a tremendous help in trying to understand the sun. It has continuous imagery in many different wavelengths, and it's also measuring like the corona through the coronagraphs. But so now actually it's okay, it's quite old. We are still using some instruments, but not all are functional anymore. And so we hope with Solar Orbiter to still fill some of the gaps, because there are still a lot of gaps in the understanding of the sun and its environment. So these are the official science objectives of the mission. Now I'm going to simplify them a little bit. So how does the sun create and control the heliosphere? So the heliosphere, as I said before, is this whole region of space which is dominated, which is influenced by the sun. What drives the solar wind? So the solar wind was this continuous stream of charged particles, which is streaming out from the sun at typically 400 kilometers per second, which means 1.5 million kilometers per hour. How do solar transients drive heliospheric variability? That's actually really about the whole variation of the activity, and also how we see this variation when we go further out from the sun. So for example, at Earth. How do solar eruptions produce energetic particle radiation? These eruptions here are mainly solar flares, as we have shown before, and coronal mass ejections, because they really produce streams of very, very energetic particles that also reach Earth, or can reach Earth. And then how does the solar dynamo work? And the dynamo is actually the system in the sun that creates the magnetic field and also maintains it. So some of the unanswered questions currently in solar physics is, how do these solar energetic particles get accelerated, and how do they propagate? So typically close to the sun, from time to time you have these bursts of energetic particles which are originating at flares. But not only at flares, sometimes when these big clouds of plasma moves into space, you get a shock front, and then also energetic particles are being accelerated close to the shock front and then travel from there. And how this works in practice, we don't really know yet, and we hope by getting closer to the sun, and so closer into the solar wind, we will understand better where they come from, how they get accelerated, because the closer you get to the source, of course, the better you can understand how it originates. Another one was the solar dynamo. So the solar dynamo actually is the mechanism through which through the plasma and the movement of plasma, so both the convection, so the continuous bubbling of plasma going out from the core to the outer layers, combined with the fact that you have differential rotation, these are one of the mechanisms that make sure that you get a magnetic field and you maintain the magnetic field in the sun. Now, the magnetic field is not equal over time. It's changing all the time. It also changes complexity, and many of those reasons are not being completely understood at the moment. So that is another thing we wanted to study. And then also the combination, well, the connection between the solar activity and the total heliospheric flux, as you can see in this graph in the blue line. Another very important question where the mission will hopefully help to solve is, how does the magnetic field look like around the poles? Because we have a lot of very good simulations already of the magnetic field, but we always look at the sun from the same plane because the Earth is orbiting around the sun. And so we can only look from that plane. So we never really see what's happening at the pole. And so when you do a model of the magnetic field, you always have these black spots, these dark spots where you kind of have to assume boundary conditions, or where you have to guess what's happening there. And so this is something that we hope to improve, that we can really measure the magnetic field at the poles, and we can really help this modeling. Also, of course, solar orbiter will sometimes be at the back side of the sun when Earth sees the front side of the sun. And this is another thing that will help us a lot in magnetic field modeling. Mission summary. When is it going to be launched? Around February 2019. We will first have a cruise phase of about 2.5 years to get to the final science orbits. And I will show you later how these look. The nominal mission will last around 4.5 years.
I don't know how anybody
can. We launch. Then the extended mission, so if everything goes fine and the instruments work fine, we hopefully get an extension of 3 years where we can move even further out of the ecliptic. Because the orbit will vary between 0.28 AU, which means this is about the orbit of Mercury. So that close we will get to the sun. And then at aphelion, this means the furthest away we go from the sun is about the Earth orbit. We will use Venus to move the spacecraft actually in an orbit which is getting further and further out of the ecliptic. So later in the mission, we will have an orbit which is inclined with respect to the ecliptic, and then twice per orbit you can see either the North Pole or the South Pole. Also, since the spacecraft moves in the same direction as the sun rotates around its own axis, you can see certain features for a longer time, because you will see the solar rotation being slowed down actually from the instruments. So this is roughly the mission profile. So in yellow, you see the different orbits. So we start in the ecliptic, so close to the plane where most of the planets move. And then slowly we will move out and we can see glimpses of the poles. And to do that, actually it would ask too much energy to actually change the orbit through systems on the spacecraft itself. So you use another planet actually to gain some force to get into another orbit. This is how the spacecraft looks like. So we have the body of the spacecraft. We have, very importantly, a big heat shield, because we come very close to the sun. So we have to protect not only the instruments, but also the spacecraft itself. We will have a boom. This is this elongated structure because we have in situ measurements who want to measure plasma and magnetic fields around the spacecraft. They want to measure them as precise as possible, but the fact that they are on a spacecraft is very annoying for them because they will get a lot of noise which is made by the spacecraft. So that's why for those instruments the best position is as far away from the spacecraft itself. So that's why we have this boom. Then we have here the antenna that will communicate with Earth. And then the other 3 antennas here are part of one of the plasma experiments and will measure the waves passing by in the solar wind. I think I can best explain the mission through this animation. This will show you a bit how the spacecraft works and all the different elements. So here you see after launch, it will deploy its solar arrays. We have quite big solar arrays because from time to time we also are very far from the sun. You just saw the heat shield lighting up, and then the thrusters, which will help us keep us position. The solar arrays, which can also be tilted because you need a lot of energy when you're away from the sun, but you don't need that much solar cells lightened up when you're close to the sun. Then here you saw the instruments being highlighted, the 3 antennas of the plasma experiment, and the boom, which is being deployed with many different sensors on. Then here you see that we will use gravity assist maneuvers. So this is a maneuver to change your orbit, and you use the gravity of another body, in this case, Venus. And from time to time, we also use the Earth itself. So especially at the beginning, we will from time to time come back close to Earth, and then Earth will help us to change the orbit. So this is an animation of how the spacecraft will move through the mission. And so from time to time, it will meet another planet to help changing the inclination of the orbit. So towards the end of the mission, we should have an inclination above 30 degrees. So we will, the spacecraft will not really fly over the poles, but it should be able to see the poles. These are the 3 periods which are most important for science, and where all the 10 instruments will take data together. So these are the times when we are closest to the sun and when we have best view on the poles. So one of the main units, of the most crucial ones, is of course the heat shield, as you can see here. And the heat shield is designed very specifically to be able to get rid of all the very hot radiation. So actually it's not a solid heat shield, it's actually different layers of material which are put together so that the heat can escape at the sides, because otherwise it would absorb all the heat. When we are close to the sun, the temperature at the front of the spacecraft can reach about 500 degrees, while at the backside it will still be minus 100 degrees. So for engineers, this is a very, very challenging mission to design a spacecraft for. So here you see the solar arrays moving away when we are close to the sun. And here you see the high gain antenna, the antenna that communicates with Earth, folding in. Well, we have a heat shield, but of course we still want to see the sun. The cameras want to observe the sun. And so you had these little doors actually in the heat shield that will make sure the instruments can still observe. And this was the end of the animation. So very quickly still, what are the types of data that we expect? We will have the remote sensing instruments, or the cameras, that will give data, that will show us images from the sun, a bit similar to what you have seen before. So the corona in 1 million degrees, then more the chromospheric part. We will see the magnetic field, and we will see the photosphere in a continuum image. I've shown them here as 4 quadrants, but those instruments will always see the full sun, of course. It's just to get them all on one slide. Then you also have specific instruments which only have a very small field of view, so they can only see a bit of the sun, but with very high resolution. So we will have much more detail of that bit. And then you also have a coronagraph on board, which will show the corona not only in visible light, but also in Lyman alpha. Then further away is, well, and there's an instrument that will look away from the sun, and that will image the CMEs coming out of the sun and moving into the heliosphere. And this is Solo-HI. And we also have another instrument, which I don't have an image here, which is an X-ray detector that will look at all the flares, all the activity actually on the sun. The in situ instruments will have time series, so that means they will have different curves where they show how the magnetic field changes over time, how the plasma characteristics change over time. And so here you just have an example of this kind of data, but from another mission. A few images to end the presentation. So here you have the heat shield, which was ready here to go into the sun simulator. So here we had an radiation force which was equal or close to what the sun will give at perihelion. So when we are closest to the sun. And here you see the model of the spacecraft during the critical design review. So where the whole design was kind of finished, and then everything gets integrated. So the heat shield again, here the whole spacecraft. You also see now how big it is with the people there. And so this is the whole model with the heat shield already attached. So in summary, we hope Solar Orbiter will address the central question of heliophysics. How does the sun create and control the heliosphere? It will make in situ measurements of the solar wind, plasma, fields, waves, energetic particles, much closer than we could do up to now, because now it's all limited to 1 AU, so close to the Earth. And then simultaneously, we will have high-resolution imaging and spectroscopic observations of the sun, not only close to the sun, but also at times out of the ecliptic plane. And it's the combination of those two sets of instruments that actually make the mission unique. And so launch is foreseen for 2019, and we all look forward to it.
Yeah, many thanks, Anik. Also, especially many thanks to you for 3 presentations today. And all this at the last moment, I have to say, really, many thanks. She was just coming back from holidays, and we were asking her to help us with that one. And I think it was an enormous help for us to have all these special presentations about the sun and the related missions, ESA missions. And with this, I don't know how is it going with. Do we have some questions on the Twitter feeds? Nothing in English, in Spanish.
Thank you. We were asked whether we can also see stars once that the totality arrives.
Yeah, I'm not sure. I think in principle, yes. I personally don't remember, because when I saw my only total eclipse in Austria in 1999, I cannot remember if I saw stars. I was so excited about it, but I cannot remember. Anik, do you remember at yours? Did you see stars at your observations?
Actually, I was also too overwhelmed by the corona itself that I didn't really look at the star field. But it is true that you can see stars, because also you can do actually a setup to kind of repeat the experiment that they did for Einstein's relativity theory, and for that you need to see stars close to the sun. But the problem is, of course, you need to have good examples of stars which are also bright. And so you will need to really do the experiment again. You need proper equipment. But so you will see stars in the field while during totality, that's for sure. But to have them very close to the sun so that you can really see the effect that Einstein predicted, for that you need a bit more equipment.
And I would say, keep in mind, if you look at the chromosphere, you probably won't see stars. But of course, you could turn around, and you're in the dark, and you could look and see lots of stars. And in this case, there were also supposed to be 4 planets that were visible, which you wouldn't have normally been able to see during the day. And so when we look at the images, we'll be able to see if we saw Jupiter, Mars, Venus, and Mercury. We're hoping to see those on the images later. And we'll see if we picked up any stars. But since we were looking at the chromosphere, chances are we won't see any stars in our images.
And I remember that preparing the observations, we were checking for bright stars to see eventually if we can also repeat the observations to prove the relativity. But there were no real bright stars close during the eclipse, at least not from the observing point in Caspar, where we are planning to go. I don't know if we have connection to the US.
It's all the gesture of the network. Now it's trying to upload it, but it's not going.
So no connection.
Can you hear us? I can hear you.
Yes, we can hear you. We cannot see you at the moment.
Can you see?
The connection is really very bad.
We will try to show you the pictures through the. I don't know if you can image or you can only hear us.
But we have no video for the moment. Very slow.
Can you hear us?
We can hear you.
Connection is really poor. The connection is really poor now. If you can hear me well, I cannot hear you. So it's quite poor. It's very,
so it looks as really that as we were making jokes about this before the hangout. We were saying, yeah, for sure that all people after the totality will send their images to Facebook, and it's not a joke. It is, I think, really what's happening. So I think it's exactly what we were joking about. So everybody is uploading the images.
And it's an interesting lesson in how your communication systems work, because your voice is sent in little discrete packets, and we're losing lots and lots of the packets. So while we're getting some noise, they can't be stitched together to make an intelligent conversation. So I don't know what the packet loss percentage is right now, but the fact that we're getting anything at all is probably miraculous, but just not enough packets are being received to be able to tell what they're talking about.
Yeah. Anything from Twitter? No? Nothing for the moment? People are busy in looking at the images instead of tweeting. Okay. So Bear just told us that one of the followers are saying us a big thank you for the Google Hangout and the live images. So this is very nice. So at that stage, we were planning to show NASA images if we have our own problems with the connection. But the problem is that we also cannot connect to any of the NASA sites. Don was trying before, and he is, I think, trying again. Bear has found something. Bear, are you in a Hangout or not? Can you please put it on the Hangout? Okay, sorry, yes. Yeah, this is a nice video. Can we just repeat it, please? So these are the live impressions from the internet. Very impressive. Some clouds. Now the totality. Very nice video. Images from the internet, from NASA.
The clouds even make it more dramatic.
So it seems that we found another NASA page which is working. So Anik will try to put it on the screen into the Google Hangout. We just lost it. Okay. Where can you repeat the one that you had before? Very nice picture from Jefferson City. Yeah. So this is
it's the White Light Telescope in Carbondale, Illinois.
Which, by the way, is interesting because Carbondale, Illinois is also going to be in the totality of the next eclipse, as the next eclipse will be roughly the opposite of this one, going from the northeast of the from the southwest of the United States to the northeast of the United States. And Carbondale, Illinois will be one of the few cities which are in the totality both times.
And that's 24, isn't it, in 2024?
Yes, they come in pairs separated by 7 years.
So we have now an image from our spectrograph grid in front of one of the cameras. So what you can here see is the spectrum of the sun during totality. So the different pictures in the different colors are just different emission lines, I suppose. Yeah, so unfortunately we have not yet recovered the processing of the images, probably also not the transfer of the images. So we have just the images before totality, 10 minutes, up to 10 minutes before totality. And then because of the lack of bandwidth, no images were transferred. Yeah, so it stops 10 minutes before the totality. On our web page, there is now one image from totality at 1742 UTC. It is unfortunately not in the center because it's probably a problem of very nice one, because of the processing. The processing was of course optimized for brightness of the sun, the normal brightness of the sun, and during totality this drops considerably. So we will probably have to reprocess the images manually afterwards. Bear is trying to tell me something. There's a nice image. David, if you switch to Bear's Hangout, there's a nice image from Hopkinsville in Kentucky. So it's a nice image here from our mask that we did with the ESA logo. And you can clearly see that from every... it's not there, sorry. So now, very nice image. There is a logo that we did as a kind of mask with the 3D printer. So you can see every hole in the mask is producing a small eclipse image. It's very nice. This is also very impressive to see. If you once have observed a solar eclipse, even under trees, if you go under a tree, the light that is going through the different holes in the tree leaves form small eclipse images. It's really impressive. I've seen this once in an annular eclipse here in Spain. So it's a very nice picture with the mask. And on our web page, you can see that some of the images are now processed. So we have an H-alpha image just after totality, and we have a visible image during totality with the corona visible. So really very nice. Unfortunately not centered, but this is probably because of the automatic processing. Because the processing routines, the automatic processing routines, what they have to do, they have to find the center of the sun image, which normally is not a problem because the sun is very bright. But in this case, the algorithm doesn't recognize probably the circular shape of the sun correctly, because you have the dark part in the middle. But anyway, I think Santa is working very hard to get the processing running again. I see in the WhatsApp that she says that the connection gets better. So a really nice image of the corona in visible light. And David is playing with the images to see if we can get just the best images. So this is one very close after totality. This is going close to totality. So this is H-alpha during totality, which of course you don't see anything because the H-alpha filter is taking away all the light, is optimized for normal sun images. I thought there was one on the west side for yeah.
Yeah, so when there would have been a very, very bright prominence of limb, then H-alpha would have seen it. Now, it may be that there are still some in the image, but we will need some more processing to get it out.
So in about 10 minutes, we will connect here to a local observing site We have some enthusiasts here also with a solar telescope on the terrace, and they will try to observe for 3 or 4 minutes the solar eclipse here locally. So in 10 minutes, we will try to connect to them and see if we can see the solar eclipse. At least the images they have are okay. So we'll try to connect to them in some minutes. So look at this nice picture now. We're getting now slowly and slowly the images process. We can connect to Wouter for a moment, who is editing out.
Hi, Misha, can you hear me?
Yes, Wouter, we can hear
Okay,
you.
good. I cannot hear you very well because there's a lot of noise here.
So can you just show us the observing
My
side?
phone is, the volume is not good enough.
Wouter, please put the telephone in landscape mode.
I'm sorry?
Put the telephone in landscape. Horizontally. Yes, please. Oh, excellent. Yes, horizontally. Much better. Please, landscape mode.
Sorry, can I have one moment of silence, please? Leo, sorry, 1 second. Michel.
Yes, please put
Hi.
the phone in landscape mode horizontally. Then we have a better image. Yes.
Like this?
Yes. Excellent.
Okay.
Many thanks.
So let me see. I can show you a little bit the picture that we're taking at the moment.
Yes. Very nice. Yeah.
So you can actually see some sunspots and everything.
Yes. Very good.
And the setup that we have is this.
Yeah.
It's a
Is
tornado telescope from Leo.
Yeah.
With a video camera here, that's mine. And an equatorial mount that we borrowed just for now.
Very good. So how many people are there?
Sorry?
How many people are there?
Yeah, let me show you. There's quite a few people. Sorry, like this. Leo, Juan, some of the students,
Yeah.
Virginia, Alfonso, and Michele.
Very good.
So we're about 15 people.
Excellent. So let's see if we can see at least some.
Sorry?
Let's hope that we can see at least a little bit of the moon.
Yes, I hope so too. I suggest that we connect again in about 10 minutes and then I can show you a little bit of the partial phase.
Okay, very good. Many thanks.
Okay, talk to you later.
Yeah. Right? Oh, very nice picture in the meantime here, after the processing. So this is H alpha. Is this visible? Yeah. Oh, very nice picture with the corona. Really very nice.
It's interesting that we don't see on the limb on the left side the coronal mass ejection that we were able to see before the eclipse. Doesn't seem to have any effect on the corona whatsoever. I have no idea why.
Yeah, me neither. But the images are really very nice. Look at those images. So this is just after totality when the light comes back. Amazing images. So I'm really looking forward to the final video. I suppose our poor guys have to continue working after the observations to get the videos done. Amazing pictures. So anything from Twitter? No more? No. Okay, at this stage, I think we can do a short resume. I think it was an enormous success. I didn't expect that much out of it. Essentially, I was quite frightened that we would not have any connection. I'm really very happy. We could see up to totality, even the Google Hangout with our guys in the US. And also the images are quite good. So I think it was quite a success. Comments?
No, I agree. I was quite surprised that the network in Wyoming didn't go down. We were able to get images and even some voice at critical points, and we're transmitting the images now. So I think from our end, you know, as far as capturing images for future use in the educational efforts here, I think it worked out great. So congratulations to you and to everybody who made the long trek to Wyoming to get these shots.
Okay, then perhaps we can use this moment, since Don started, to say thank you to all the people that were doing a great effort here.
Michel?
Yeah, let's just connect again to Wouter on the terrace.
We have a partial phase at the moment.
Yes, we have it. We have it. Excellent. Congratulations.
Thank you very much. Oei, feedback.
So let's stay with you until it finishes, because I suppose that the sun is just on the horizon. Can you just show us the sun directly? Yes, just on the horizon. So very nice. So this is really a nice way to finalize the event. I think it's really great to see this. So let's just stay with Wouter these last minutes of the solar eclipse. See the moon coming in on the sun. And then, of course, the moon shadow will go away.
We are watching here also with the solar eclipse glasses, and people can actually see the little dent in the moon. So that's pretty cool.
Yeah, really very nice. So also a great thank you to you, Wouter, for this effort.
Well, it was Leo and me together. Thank you. Michel, sorry, I'm going to hang because I want to try and see it with my own eyes also.
Okay, very good. Many thanks, Wouter.
You're welcome, and enjoy the rest of the show.
Yes, and if we coming to saying thank you, I would like really to thank all the people involved. This is especially our colleague Miguel Perez Ayuca, who was the driving force behind the whole event, and probably without him, we would not have done it. And then, of course, the team that was going with him to the US. So it's Abel de Burgos, Manuel Castillo, Joe Sender from ESTEC, and of course, all people involved here locally. So we have Santa Martinez, who was taking care of the processing while she's still on holidays. So she's doing it from at home. I'm also here. Then we have David Cabezas, our producer, who is sitting in the back. Don, our colleague here, was helping a lot during the whole event with all types of things. Anik, she already left, but it was a great support from her, since she's the specialist on all things about the sun. And she did 3 presentations today. Also to David Parado from INTA, who was giving the presentation about the solar eclipses and the historical background, which he did together with Guillermo Infiesta, who is our trainee here at the CESAR initiative. Also to Bea Gonzalez, who was taking care of the Twitter stuff. Asun Casado, Emily Baldwin in ESTEC, who is responsible for the ESA Science Twitter, and Rebecca Barnes, who is also in the education project. So many thanks to all of you. I think working together made this a big success. We have also to thank probably the mobile providers in the US that were not collapsing and were making it possible for us to transfer most of the images. You can see, if we switch to the, let's switch back to the Google Hangout to the live images, so you can see some more of the images there. So I think it was a great event. It would be nice, before we close it down, to have a last word with the people in the US. So I don't know if it's possible to connect. Okay, so it seems that we cannot get a connection to the US. Everybody is uploading the images to Facebook. So as I said before, many thanks to all the involved people. I think it was a great success. And I hope to see you at the next event, which will be, I think, a solar eclipse in 2019. Let me just check. I think we have in 2019, we have 2 events. We have a solar eclipse, a total solar eclipse which is going through Chile and Argentina. And I think we also have a Mercury transit again. Do I hear something? Here's something. Perhaps we are lucky in the end, just get the last connection. Yeah. Hello?
Hello?
Hello, can
you hear us?
Yes, we can hear you. So, congratulations.
Can you see us?
Oh, thank you. Thanks. It was really amazing. Can you see us in the screen?
Sorry, can you please repeat?
Can you see us?
We can hear you.
Can you see us?
We can hear you. We have no video, but we can hear you.
Okay, then we will talk. So,
congratulations. I think it was a big success. We were not expecting to have such a good Google Hangout connection up to totality. And also the images were coming in regularly up to totality.
Yes.
So we are really very happy here. And you have done a great job. Can you just summarize your impressions about the event?
Yes, but I don't know. It's very emotional first. I mean, seeing the kids is very emotional. You get first this feeling of coldness, no, before totality. It's really, you really feel that it's cold and colder and colder and colder. And you know, I mean, we're taking the computers and it's a bit, we're getting nervous. And as the time was progressing, we also had in mind, of course, all the work we had to do because it was quite changing several settings, the cameras, filters, and stuff like that. The sequence of images, we have not done this before. Many things could have gone wrong. I was extremely happy in Zeus. Technically, I think things went really, really good. I think all of us were several different things. I think we are all happy that we also all themselves. Everything went and I'll go to the images. You haven't seen all of them because that's transmitting all of them. That is breakdown of the network and everything worked. One year before I was working. So, but that was really nice that it could happen. So that's fine. Then I was in the more personal feeling. I don't know, you have never seen anything like that. I think it's the best astronomical I've seen. The most impressive. Wow, I don't know. It's really dark, dark stars.
Miguel, we cannot really hear you, unfortunately. The audio quality is really very bad. And we also don't have any video image. So at this stage, I think we just want to thank you and your team again for the excellent performance. And we hope to see very soon the compiled images from the total eclipse. And with this, I would say also to our spectators, many thanks for following us and staying with us, even with the small technical problems that we had from time to time. And I hope to see you next time.